Hello, my name is Kayo Yuan, and today I will be presenting our work on signed coreference resolution. To begin, coreference resolution in natural language processing is the task of identifying all references to the same entity in a discourse. So in this example, we have I and me that refer to one entity, Alice and she to another, and Bob and he to a third entity. Coreference resolution is a critical component of natural language understanding and higher level NLP applications, including information extraction, text summarization, and machine translation. Yet this task is completely unexplored for signed languages. So in this paper, we will explore the task of coreference resolution in signed languages. I will begin by presenting how coreference is established in signed languages through pronominal pointing signs. Sign linguists generally recognize the existence of signs that serve a function similar to that of pronouns in various signed languages. Reference of pronominal signs are often established in the signing space, which is the three-dimensional space in front of the signer that is used to produce signs. When using pronominal pointing signs, signer can point to the actual location of the referent if the referent is in the same room, for example, such as towards themselves for I, towards the identity for you, or towards an entity in the same room for he, she, they, it. And for entities that are not present, the signer can assign a particular point in the signing space to the entity, then point to this point for all subsequent mentions of the entity. We call these points in the signing space a locus. To give an example, the two characters Alice and Bob are introduced by fingerspelling their names on the left and the right side of the signer respectively. Then, instead of fingerspelling their names each time the signer refers to the characters again, the signer can simply point to the locus assigned to the character, which can save the signer a lot of time. This is similar to how she and he can be used in English to refer to Alice and Bob, but in signed languages, the visual space is heavily exploited to make the referencing clear. As a result, the meaning of pronominal pointing signs is not stable, and it highly depends on the context. And therefore, coreference resolution is necessary to identify the antecedent of these signs. To better understand the complexities of pointing signs, we can also try to compare pointing signs to pronouns in spoken languages. For instance, in English pronouns such as he, she, they carry some meaning on their own. Removed from context, we can still infer the gender or the number of the referent. However, pronominal pointing signs have the same features of hand shape when they are removed from context, so we cannot infer anything about the reference of these signs. On the other hand, while the same pronoun she can refer to two or more distinct entities at once. So in this example, the two pronouns she refer to separate entities, but using the context, we can infer that the first she refers to the mother and the second to Alice. In signed languages, a given locus refers to at most one referent at a time. But this still comes with more complexities because, first of all, the same locus can be reassigned to different entities during the discourse. As an example, we might have this locus that refers to Alice at first, but then the signer can reassign this locus to Bob later by first signing his name, then pointing to this location. A signed entity can also be assigned one locus to another during a given discourse. So for example, if Bob is at the store and the store is assigned a locus on my right, but then Bob returns home, which is assigned to a locus on my left, and the locus for Bob also changes from right to left. Therefore, models must be able to handle long-term dependencies to be able to detect and keep track of when there's a change in entity locus assignment. We believe that it is important to study signed coreference resolution in natural language processing because some theories of coreference in spoken languages may be extended to signed languages. So this further motivates the development of linguistically informed natural language processing models for challenges in processing signed languages. Another motivation is that signed languages can also help us better understand how to process multimodal communication in general. For example, iconicity can sometimes play an important role in the spatial grammar of signed languages. Loci and signed languages can simultaneously have a grammatical function, such as pronouns, but also a logical function, where some of the geometric properties of signs and signing space can reflect those in real life. Therefore, studying the integration of iconicity and situated reference in signed communication will provide valuable insights in understanding how to process grounding in spoken languages as well. And we also believe that it is important, it is extremely important for us as NLP researchers to ensure that language technologies are accessible to all communities, including deaf and hard of hearing communities. And solving coreference resolution is an important step to provide higher applications of signed technologies. I will now present signed coreference resolution as a novel challenge in natural language processing. We formalize signed coreference resolution by decomposing it into two tasks. So first, we have mention detection. We're given a video of a person signing. We extract all mentions in the video, that is the signs or the group of signs in the video that refer to some entity. And next, we perform coreference resolution over the mentions. So after obtaining the set of mentions, we then identify the coreference assignment of each mention, where all mentions referring to the same entity is assigned the same coreference label. Since this is a novel challenge, we develop a small data set of assigned language with gold coreference labels to be able to evaluate our models. And we base our data set on the existing public DGS corpus, which is a data set of 50 hours of annotated dialogue between native signers of German Sign Language. And since the public DGS corpus does not contain explicit annotation for coreference, we also hired annotators to enhance the glossal annotations for from the public DGS corpus to construct our data set. And to do so, we developed an annotation interface of coreference resolution for signed languages, which is pictured here. And then the annotators can submit their annotations by highlighting all glosses shown that refer to the same entity as the underlined pointing gloss. We publicly released the DGS coref dataset, which is a subset of the public DGS corpus that has been enhanced with annotations for pronominal indexing coreference. DGS coref comprises 60 minutes and 30 seconds of signing and 288 signed sentences with 1,458 total glosses, including 196 different pointing signs. In this example, the glosses and translation are from the original public DGS corpus. Then DGS coref has the additional annotation that the two index signs are coreferent. Now I will present the unsupervised model we propose for signed coreference resolution. In our approach, we modeled the document as a directed labeled weighted multigraph, where the gloss tokens are the nodes of the graph. Then we construct edges between mentions if two mentions verify relation, and then we assign different positive and negative weights to these mentions depending on the relation. Then clustering is applied to the resulting multigraph to obtain the entity groups contained in the document, where nodes with degree 0 in the graph are non-mentions. We propose 6 heuristics as positive relations that indicate coreference. So first, the I and I heuristic is when the two signs are produced by the same signer and point to the signer's chest. Then U and U, the two signs are produced by the same signer and point away from the signer's body towards the addressee. I and U, where the two signs are produced by different signers, one points to the signer's chest and the other points away from the signer. Temporally closed index, where the two signs are indexing signs produced by the same signer and they have less than 10 signs between them. Noun phrase, if this is when an indexing sign has no other indexing signs within the previous 10 signs, and then this is indicated as maybe coreferent to the temporally closest previous sign, that is a sign that is not a verb produced by the same signer. Then we have spatially closed index, where the two signs are indexing signs produced by the same signer, and the Euclidean distance between the two locations of production is less than 50 pixels. And we also add 4 constraints to coreference as negative relations, where we rule out two mentions for coreference if they have any of these negative relations. So first, the negative I and I is when two signs are produced by different signers, but each point to the signer's chest. U and U, where the two signs are produced by different signers and point to the addressee. I and U, where the two signers are produced by the same signer, but one to the signer's chest and the other points away from the signer's body. And then we have different person, where one sign either points towards the signer's chest or towards the addressee, and the other sign that is signed by the same person points to a third person. And we have spatially far index, where the two signs are indexing signs that are produced by the same signer, but the Euclidean distance between the two loci of production is greater than 100 pixels. Now I will describe how we assign weights to the graph edges depending on each relation. For all negative relations, we assign the weight -infinity as they are hard constraints for coreference. And for binary positive relations, we assign a fixed weight of 0.5. Then for the temporally closed and the noun phrase relations that depend on the temporal proximity of the signs. So if the two signs have t signs between them where t is less than 10, then the assigned weight is 10 minus t over 20. And for spatially closed index, if the Euclidean distance between the two signs is s, where s is less than 50, then the assigned weight is 50 minus s over 50. We apply 1 year's neighbor clustering on the obtained multigraph to identify the coreference signs. And for every sign, it is dimensioned if it has at least edges to another sign where the sum of the edges is strictly positive, then this sign is coreferent to the sign whose sum of edge weights is maximal. Finally, I will discuss the results of our model on signed coreference resolution. We evaluate our system on commonly used metrics for coreference resolution in spoken languages, and we achieve a mean F1 of 50.54 across all indexing signs. Overall, we achieve a high mean of 92.2 on I and U signs, which is expected as they contain low ambiguity and meaning. And on index signs, where the model must keep track of spatial coherence and discourse and resolve different loci, we achieve 26.9 mean F1, which shows that there is still much room for improvement to this ambiguous third-person indexing signs. And our paper also contains qualitative examples of what our models are able to achieve or not. So to summarize, our paper presents a new challenge in natural language processing called Signed Coreference Resolution. We released an annotation software and a new dataset of coreference in German Sign Language. Then we proposed an unsupervised continuous multigraph model with a set of sign linguistics informed heuristics to perform signed coreference resolution. And our coded data is publicly available to help underpin future research in this task and further tasks in sign language processing. Thank you for your attention.